Chapter 14, Exercise 1 is asking you to provide an IUPAC name for some ethers. And IUPAC stands for the International Union of Pure and Applied Chemistry. It's a club, a chemistry club, that came up with a systematic way for naming organic compounds. And you would remember from Organic Chemistry 1 that a name has at least 3 parts: a prefix that tells you about the number of carbons in the molecule or in the main chain of the molecule, the infix tells you about the bonding, and the suffix tells you about the functional groups. So, when you name ethers, you'd recognize an ether because it would have an oxygen with carbons on both sides. And in organic chemistry, a capital R stands for any carbon chain. So here you have an oxygen with carbon chains on both sides. The first thing you'd want to do is to find out which carbon chain has more carbons. So here, we have our ether oxygen in the middle. On the right of that, you have 1, 2, 3 carbons, and on the left you have 2. So the right is the longer chain. And once you have the longer chain, you're going to name that as the backbone. And the ether, along with the other carbon chain, is going to be named as a branch. So to name that backbone, the first thing we want to do is to find the prefix. There are 3 carbons, and so the prefix will be prop. In that carbon chain, all of the bonds are single bonds, and so the infix is going to be AN. All of these bonds here are single, so the infix will be AN. And because ethers are named as a branch, they aren't going to be included in the backbone name. In this circled area, the circled area in blue, that backbone only has carbons and hydrogens in it, so it's a hydrocarbon, and the suffix is just going to be E. So the name for the backbone here, this circled area, is propane. Okay, that has one branch coming off of it, and that's going to be this whole thing here. So the smaller carbon chain and the oxygen are going to be named as what's called an alkoxy branch. The alk is going to refer to the carbons in this smaller chain. And oxy will always stay the same. That's just telling you that you have that oxygen, that ether oxygen there. Now here, because we have 2 carbons, the prefix is going to be F. And because we have that oxygen, it's oxy, and so the name for that branch would be ethoxy. One last thing is we have to say where this branch is attaching to the main chain, and you can see that it is connecting on carbon number 2. So this would be 2-ethoxy. So you take that branch name, you put it in front of the backbone name, and the name for the whole compound would be 2-ethoxy propane. So that would be that answer for there. Okay, for B. So similar procedure. First step, we want to look at we recognize the ether oxygen, because anytime you have an oxygen with carbons on both sides, remember that capital R is any carbon chain, then you have an ether. So we recognize that ether oxygen, and once you know you're dealing with an ether, you look to the left and the right and count up the number of carbons in each of these branches. So on the branch to the right, you'd have 2 carbons, and in the carbon chain to the left, you'd have 3 carbons. Because the carbon chain on the left is larger, that is going to be your backbone. So we'll circle this, just the carbon chain. That's the backbone for this molecule. And before we worry about any of the other things that are not in the circled area, the branches, you want to name the backbone as if it didn't have any branches. So here we have 3 carbons. The prefix for 3 carbons is prop. In that carbon chain, these are all single bonds, And when you have all single bonds, the infix is AN. And also, within that circled area, you only have carbon and hydrogen. And so it's a hydrocarbon, something that's made up of only hydrogen and carbon, and so the suffix is E. So again, our backbone is propane. Now that we have the backbone named, we'll want to name each of the branches. And first, let's start with the ether branch. So we'd recognize that ether oxygen here, and then the carbon chain. The smaller carbon chain has 2 carbons, and so the prefix for it will be F. And because we have that oxygen there, it's F-oxy. So the name for that branch is F-oxy. Now we'd have to see where it's attaching to the original chain. Now when we numbered this, we numbered it right to left. Theoretically, you could have numbered it left to right, but you always want to number the backbone chain to give the branches the lowest numbers. So for example, we could have numbered it like this. Notice if we number it in the way in black, we'll have a branch at carbon number 1, and we'll have a branch at carbon number 2, whereas if we number it in the way that's red, we'd have a branch at carbon number 2, and a branch at carbon number 3. You want to go with the way that gives you the lower numbers, so that's the black way. That's numbering it right to left. So we'll number it right to left here, and that means that the the ethoxy branch is coming off of carbon 1. So it's 1-ethoxy, and the chlorine, the Cl, excuse me, is coming off of carbon 2, so that's our first step in naming that. So with the halogens are all the elements in group 7A, if you look on the periodic table. And you'd have fluorine going from the top to the bottom, fluorine, chlorine, bromine, and iodine. And when those are branches, you take the first name from those elements, so fluor, chlor, brom, and iod. And then you just add the ending O. So fluoro, chloro, bromo, iodo. Those are the names when those are branches. So here we have chlorine, so it's going to be 2-chloro. First syllable and then an O. All right, we have our two branch names, and we have our backbone name, and we could even put them in order. The backbone name always comes last. When you're ordering the branch names, you always do it alphabetically. So C here comes before E, so 2-chloro will come before 1-ethoxy. Always between numbers and letters goes a dash. Okay, so far we have 2-chloro, 1-ethoxypropane. There's just one last thing to add here, and that's the stereochemistry. You should always watch out for stereochemistry if in the problem you ever see a solid wedge or a dashed wedge, because those are telling you about the 3-dimensional arrangement of the bond. If you have a regular line, then the bond is in the plane of the paper, so in the plane, not coming out at you, not going away from you. If you have a solid wedge, it's coming out at you, and if you have a dashed wedge, it's going away from you. So we see that here, and that's a sign that you might have a chiral center. So the rules for a chiral center is an atom that has 4 different sides. The carbon forms 4 bonds, so if it's bonded to 4 different things, then it's chiral. And what that means is anything that has 4 different sides comes in 2 versions, a left-handed version and a right-handed version. And those 2 versions fit into pockets differently, so they behave differently, they have different properties. So in the name, you want to say which version you have so that you know the behavior for the specific molecule in front of you. And you can find out whether it's the left-handed version or the right-handed version by using the Kahn, Ingold, or Prelog rules. This is more review from Organic 1. So the CIP rules. The first step is to identify the chiral center. So here we've got that. That's the atom that's bonded to 4 different things. You can tell because you've got chlorine, you have this whole thing to the right, you have a methyl group to the left, and invisibly you would have a hydrogen going away. Another thing to note is that on a tetrahedral molecule, you'll have 2 bonds that are in the plane, one coming out at you, and one going away. So that's how I knew that this hydrogen was going away, because I already had the 2 in the plane and the one coming out. So I have 4 different things on this molecule, or on this carbon right here, and so that means that it is chiral. It comes in 2 different versions, a left-handed version and a right-handed version, that behave differently because they fit into different pockets. So once you have identified your chiral center, you want to list the 4 things that it's attached to from the highest atomic number to the lowest atomic number. So remember, the atomic number is the number at the top of the box on the periodic table. The one that has the largest atomic number gets the number 1, and the atom that's bonded to the chiral center that has the lowest atomic number gets the number 4. So here we have hydrogen. If you look on a periodic table, the atomic number for hydrogen is the lowest on the lowest. It's the number 1 at the top of the box. There'd be a 1 up there. You would have a carbon, and there'd be a 6 there, another carbon here with a 6, and then you would have a chlorine. And if you looked at the top of the box of the chlorine, you'd see that this number would be bigger than 6. So it has the highest priority. It would get the number 1. The hydrogen has the lowest number, and so it's going to get the number 4, because that 1 is lower than the 6's. Okay, these 2 carbons tie, and whenever you have elements that tie, you want to make a small table. So I'm going to make a table for this carbon on the right, and another table for the carbon on the left. And you'll list in that table, in order of descending atomic number, the 3 things that this atom is connected to. So it's connected to an oxygen and to 2 hydrogens. The highest atomic number here is oxygen, and after that would come the 2 hydrogens. And then if you look at this other second carbon here, that is bonded to 3 hydrogens. And because those all have the same atomic number, it doesn't matter what order you list them in. Once you have those 2 tables, you look at the top row first. Only if the atomic numbers for those elements tie would you go to the second row, and only if those tie would you go to the third row. Here they don't tie. The oxygen, the atomic number for oxygen is higher than for hydrogen, and so this carbon here has a higher priority than the carbon on the left, and so it gets the number 2. And the carbon on the left would get the number 3. Okay, so we identified a chiral center. We determined the priorities of each of these, of the 4 things attached to the chiral center based on the atomic number. The highest atomic number got the number 1, the lowest got the number 4. You want to make sure 4 is pointing away. We'll talk about what to do if it's not, but notice that it is here. If it's pointing away, then all is right in the world. You can go on to the next step. Now, for the next step, you ignore 4, and you go from 1 to 2 to 3. So, if we start at 1, we go to 2, and then we go to 3, you'll notice that you're going counterclockwise. And if you're going counterclockwise, that is by convention a left-handed molecule. and it's called S. S is coming from the Latin word for sinister, which just means left in Latin. If it were a right-handed molecule, it would be R for rectus, or R for right. And you can remember which one is which, because if you go clockwise from the top to the bottom of an R, you have to go clockwise. If you go from the top to the bottom of an S, you have to go counterclockwise. So here we went counterclockwise, and this was S, or a left-handed chiral center. The stereochemistry always goes in the very front of the molecule, so you'd have an S there, and always between letters and numbers goes a dash. So the name for this molecule would be S2-chloro-1-ethoxypropane.